a number of different industries. Some of the work that I'm talking about has in fact been supported by a couple of exciting DARPA projects that we've been involved in, software area control. And the JFAC project. This laptop seems to have a mind of its own, so you'll have to excuse me once in a while in the course of this presentation, perhaps. So here's the outline of what I want to talk about. I'm going to start by giving you some examples, some illustrations from a few domains about how, when we talk about automation and control, there's over the course of decades and almost a century in one case anyway, there's been this development from talking about loops to talking about enterprises. And then I'll turn to some specific discussions on the topic of autonomy, which I think is kind of central to many aspects of enterprise optimization. And from there, we'll lead into some discussion of what I think are selected directions that are important for more research and development in automation and control systems. And then I'm going to indulge in some little brief philosophical speculation that some of you are likely to think is unwarranted, but being plenary speaker gives you some license, so you'll have to bear with me. And finally, I'll just conclude with some thoughts. So first of all, let me briefly review some aspects of the history of commercial aviation. Let's go back to 1903, when Orville Wright flew the first aircraft. And in fact, as you may expect, there wasn't really much automation and control, automatic control behind the flying of this aircraft. In fact, Orville Wright was the sensor, the information processor, and the actuator. And it took us almost 30 years before we had some significant degree of automation in the aircraft. And the picture that's shown at the bottom left here is the Boeing 247 aircraft. It was first commissioned in the early 1930s. And it provided, for the first time, what we now refer to as an inner-loop flight controller. So here, there was in fact an automatic system that would take information from sensors that were on board the aircraft and would take some desired state information from the pilot, and it would compute the actual control surface movements that were required to get the aircraft to behave in the desired way. So about 20, 30 years before that particular development happened. Then in the 1950s, with the development of the 707 and the DC-8, we went to the next stage in automation and integration of control. Now we had another box shown here on the upper left-hand corner, and it's labeled the handling qualities controller. And what an aircraft with the handling qualities controller could do, or what it required of the pilot now, was simply that the pilot could indicate a new heading command whenever a new heading was needed. And now this handling qualities controller would output a desired aircraft state, and this desired aircraft state would then go to the inner-loop flight controller, which would then compute the control surface movements. So the handling qualities controller essentially had some criteria related to how you want to transition from one heading to another heading in terms of the comfort of the passengers, fuel economy, wear and tear on system components. And so that was in the 1950s. And then in the 1970s and the 1980s, we saw the development of flight management systems. And in fact, all modern commercial aircraft have flight management systems, and all that a pilot needs to do with these flight management systems is he or she needs to input a route. And this route is input by way of identifying waypoints. So at what time do you want to be over what particular location at what particular altitude? And that's all that the pilot needs to specify, and the automation takes over from there through these various integrations of different loops. But that's already actually 20 or 30 years old technology, and there's a lot of interest in the commercial aviation industry in discussing where to go next, what's the next significant advance that is occupying the interests and resources of many people in R&D activities in this industry, and in related academic circles too. And it turns out that people are less interested in what the next layer of automation is in terms of the operation of a particular aircraft, and we're starting to think now about the commercial aviation enterprise. And this particular figure shows a simplified function structure for air traffic management, and it's taken from a recent paper by some Boeing authors. And actually, you'll see at the bottom right-hand corner the citation for this paper. And because of this broad brush treatment I'm doing here, I won't really be talking in any detail about any specific piece of work that I mentioned. However, at the end, I'll show you a URL from which you can access the full references. So that's one reason just to try and stay till the end of the talk. So everything we've talked about so far in terms of the levels of automation and control really fits into this box at this edge over here, the aircraft guidance and navigation box, and with one loop. But what's of interest now are all these other boxes to the left. So we're interested in sector traffic control, sector traffic planning, facility flow planning, national flow planning, even flight planning take into account airline flight schedules. And we're interested in automating all of these layers of activity that are related to commercial aviation enterprise. And you notice the time frames involved in some of these activities as well. They go up to days when you think about the airline's flight schedule and various other durations, all the way from the minute level dynamics involved in the most of what I was talking about before to this point of flight planning. You'll also see some feedback, and in fact in this case the feedback to the sector traffic control and sector traffic planning boxes is coming not from just one aircraft, but it's coming from the whole set of aircraft that happen to be flying in that particular sector. And one of the points that the people who wrote this paper make is that, in fact, this feedback is rather limited, and in order to really have better operation and greater optimization of commercial aviation, you really need to be able to provide more meaningful feedback at this higher level of planning activities too. So several other interesting aspects of this figure as well on the paper, but I'll just move on. And I'd like to next talk about another application domain, entirely another industrial domain, and this is process control. And let's start by looking at what I think it's safe to say is the foundation for all process control, and this is the PID controller. And here's the equation for the PID controller. I have to warn you that it's one of the very few equations you'll be seeing in this talk, so if you're looking for technical content and technical depth, you have to resort to the papers that I'll be citing. So this is the PID controller, and an obvious question to ask if you're into PID control is that where does the PID controller belong when we talk about the future vision of automation in the process industry? Now, certainly one thing to remark is that PIDs are everywhere, in fact not just in the process industries, but in many other industries, in the aerospace industry as well. But being everywhere is one thing, and being the focus of the future vision is something else. So where are we going in terms of the vision of process control? So this picture here shows one view of what people are focusing on, or have been focusing on. And it's one unit in an oil refinery. It's called a Solvent Dewaxing unit. It actually consists of a number of different pieces of equipment. There are chillers, there are heat exchangers, there are flash towers, there are strippers, there are other things. And it's all a rather complex unit in itself. It can have perhaps as many as 100 or more sensors and actuators involved that you have to think about controlling in some coordinated way if you really want to operate this particular unit optimally or near optimally. And any individual PID controller is actually a rather small piece of the puzzle, and that's shown with that little highlighted circle on the center bottom, the right bottom. So it's still kind of part of the picture, but it's not really a big part of the picture. But actually, the issue is that even problems at this level of complexity and scale are now very readily solved in the process industries, and this is well within the state of the art. This is actually fairly established technology to be able to solve a problem at this scale with one multivariable controller. These controllers tend to be more effective controllers. So from the point of view of future vision, actually this is already very readily available. So what the most of the activity in terms of development today is a whole refinery scope of automation. So now we're interested in the operation and optimization of an entire refinery. And here's a schematic of a rather simple refinery actually. On the left is crude oil coming in, and on the right there is the whole set of possible products that a refinery can make. So this includes liquefied petroleum gas for cooking, it includes gasoline for airplanes and automobiles, kerosene for farming, furnace oil, diesel oil for railroad trucks, fuel oils for factories and ships, asphalts, refined waxes, all the way down to coke. And there are a whole number of individual units that are involved in the production of the outputs of the products of a refinery. And overall, a refinery can have as many, in fact, this is in some ways a conservative number, 10,000 sensors and actuators. And now when you look for any individual PID controller, it's a yet smaller piece. But so this is actually the focus of a lot of development that's already underway in the process industries. And in terms of what people are thinking about as the next major step, it's actually a step beyond this. And now we're thinking about, sorry about this continued problem here. Now we're thinking about the supply chain as an enterprise, as a focus for automation technologies. So when you think about the supply chain in this context, you need to think not about one particular refinery, but think about a company like ExxonMobil, for example. Now, ExxonMobil has many refineries that are all over the world, so they have global production facilities. They have to satisfy demand for very many different consumers all across the world as well. And they have to take into account in their planning and in the operation of their refineries and in the operation of the other associated activities that are related to refining, various aspects of the supply chain of petroleum refining. And so you have to take into account what demand there is for your product in different parts of the world. You have to take into account how you're going to transport your product from individual refineries to the places where it's needed. You have to be able to predict demand. You have to be able to have some plan for getting raw materials into your refineries. You have to have some understanding of where the raw material is going to come from, which ships, which pipelines. You have to have transportation and production schedules accordingly. And all of this needs to be tied in together with the operation of any individual refinery, and you want to, in fact, think of this as an overall dynamic system and optimize the operation of any individual refinery from a dynamic perspective. And now, actually, if you try and find any individual PID controller, it's almost imperceptible. So those two treatments of some industrial domains from the point of view of enterprise optimization. And from that, let me lead on to just sort of briefly mentioning three other areas. On the top left-hand corner of this view graph, you'll see a schematic of a particular, showing this the screen capture from a particular tool that we developed for the sort of a prototype for the electric power industry. And when you think about the deregulated electric power industry in this country or in many other countries now, it's actually a rather complex problem. And if you're a player in this electric power industry, let's say you're a company and you own some generation capacity, and you want to think about how should I run my generators, which means what output I should produce for them, and it also means what price should I ask for that electricity that's being generated. And in order to solve this problem in the right way, you cannot just do this in isolation from everybody else and from your competitors and customers. So you have to think about what they're doing, what competing companies there are, what are their generation capabilities, what loads are you all trying to satisfy, who owns those loads, can you ink some kind of consolidated deals with them. And at the bottom of it all, you have to worry about the transmission infrastructure, which imposes very hard physical constraints on how much power can be shipped at any time from one source node to one sink node. So again, a lot of interest in enterprise optimization from this angle as well. This picture on the right-hand side is actually taken from a recent and rather exciting DARPA project in which the explicit objective is to improve the stability and control of military operations. And this particular view graph, I'm not really too familiar with the history of it, but it shows this particular battlefront with the Red River flowing through this area and this little town called Redrovia that's under attack by the blue forces. I guess since it's the Red River, it seems almost like Minnesota is attacking North Dakota, but I'm not really sure that was the intention. But anyway, the idea here is that you want to think about the whole operation of a battle as a dynamical system. You want to be able to predict the outcomes of specific strategies and tactics that you are attempting to engage in, and be able to do this in some kind of optimal fashion, always taking into account the inherent uncertainty associated with dealing with something like this scale. And at the bottom left-hand corner, we have an architecture for facility management system, and by facility management we mean here the management of large commercial buildings such as this hotel or even multi-building complexes like universities or some large hospitals as well. And there's a particular box shown here labeled the EBI for Enterprise Building Integrator. This is actually a specific product, and its purpose is to tie together many of the aspects of operation of a large commercial building. So these aspects of operation include load management, which loads should be run at what time. It includes even things like elevator management, fire and security systems. And the other thing that's touched on in a little bit more detail in this particular view graph is this notion that through this enterprise building integrator, you can decide where to draw power from at any time. So If you're a large commercial building, you can draw power from the utility, or you can draw power from your internal turbine generators, and you may have a set of those. Or I guess in some cases, you can choose to draw power from neither and suffer a blackout for a half hour or something like that. So from this talk of enterprise optimization, let me now move to discussing this notion of autonomy. And I wanted to spend a little time on this because I think this whole notion of autonomy actually underpins a lot of the discussion of enterprise optimization, yet there are some twists to that as well. So let's go back to commercial aviation. In 1945, this new state-of-the-art aircraft was initiated, and it made the inaugural Bombay to London flight. And this was the Lockheed L749 Constellation, and it flew with a 5-man crew. It had a pilot, a co-pilot, a flight engineer, navigator, a radio operator. 50 years later, the Boeing 777 came along, and it can fly with a two-person crew. In fact, many aircraft do that now, just a pilot and a co-pilot. So in the course of 50 years, we went from having a cockpit crew of 5 men to a cockpit crew of 2 people. And you can ask the question, how big a cockpit crew will we have 50 years hence? And of course, the linear extrapolation suggests an answer of -1. A similar argument can be made in industrial processes as well. Many of the companies that we deal with who are in the business of running different types of industrial plants are always emphasizing the need to reduce their operational staff in plants. And one metric, in fact, that's often used is loops per operator. You want to be able to run your plant with as few operators as possible, so this loops per operator measure, given that the loops are constant, is actually a useful measurement in the minds of the industry of the degree of automation. And I was actually meeting some couples now a couple of years ago with some people from a particular refining company who were saying that they currently run with about, I think it was 150 loops per operator, and they want to move to 500 to 1,000 loops per operator in the near future. And some data bears out some of this anecdotal evidence as well. So data from the US refining industry is shown here, statistics from that. In 1980, the refining industry employed 93,000 operators, and total refining production was 5.3 billion barrels. By 1998, the number of operators had been reduced by over a third, even as refinery production had gone up by 20%. I was giving a version of this slide at another conference recently, and in that version, I sort of expressed some skepticism about whether we'd ever get to the point of having significant plants running without any operators. And after the talk, the chief engineer of one chemicals company came up to me and said, I have to tell you, we actually have 3 plants right now that are running without any on-site operators. I have to admit, my first response was, I hope they're not in my neighborhood. But that seems to be the trend, so rates of operation is something we may see sooner than we think. Autonomous systems are, of course, very important for military applications too, and this particular slide is courtesy of the Air Force Research Lab, and it shows a roadmap for developments in uninhabited autonomous vehicles, UAVs, starting from the development of the Lightning bug, which was C-130 launched target drone, completely remote controlled, all the way to the projected development about 20 years from now of uninhabited autonomous strike vehicles. And it's a rather interesting roadmap. I'm not really going to dwell on it too much, but you'll notice one thing, that as this progression in sophistication and relative level of autonomy, as shown on the vertical axis, progresses, there's more and more interest now in thinking beyond an individual vehicle into thinking about the coordination activities of multiple vehicles. Relative level of autonomy, by the way, is relative to a human pilot, and there aren't too many human pilots I know of who will say that in 20 years we can achieve the same level of autonomy that we can with human pilots with automated systems. But nevertheless, some people seem to have that as a goal in mind. And with talking about multiple vehicles, there are similar examples that can be drawn from the terrestrial domain as well. And probably many of you have probably seen pictures such as this. This is from a driverless tuning demonstration that was conducted on I-15 in San Diego a couple of years ago. 7 cars traveling at highway speeds, maintaining very close distances to each other, and without any human steering them or providing any other kind of control input. In fact, one colleague of mine, whom some of you might recognize, was sitting in one of these cars. I think he was reading a newspaper behind the steering wheel, talking on his cell phone. So that's one question that arises as you start thinking about this progression toward autonomy in all these different areas is, why are we doing this? What's driving industry and government to think about increasingly autonomous systems? So here are three answers. The first one, in some sense, is rather obvious. We feel we can improve the performance of our engineering systems by taking the human out of the loop. This particular photograph shows in the background a paper machine. Now, those of you who aren't familiar with paper machines, they're actually really incredibly sophisticated and complex and high-performance systems. When a paper machine is running normally, it's producing a sheet of paper that's something like 30 feet across, and this paper is being produced at something like a mile a minute, so 60 miles an hour. And the thickness of this sheet of paper is controlled to within microns. Now, the only way you can achieve that level of performance is by keeping the human well out of the loop. And you see in the foreground of this picture an operator who seems to be staying well out of the loop. The right-hand side shows another twist on this question. You may think that performance is everything, but in fact, you can think of examples, and it's interesting to think of interesting examples where we use automation, even though from a purely performance perspective, the automation really isn't as good as the manual solution would be. So I'm referring here to that obsolescent human who used to be standing on a platform in the middle of intersections of traffic or directing traffic. And from the point of view of performance, this human has much more sensing capabilities, much more information processing capabilities, much more actuation capabilities than your typical traffic light. And yet we choose not to use the human, and we choose to use the traffic light. It's really for performance purposes. Of course, we have to achieve some minimal level of performance with automation in cases like this. And I was in Rome for the Hybrid Systems Conference a couple of months ago, and I noticed that in Rome they still use traffic policemen rather than traffic lights a lot of the time. So our level of automation still hasn't quite reached the degree of sophistication that can allow it to function even minimally in places like that. And the final picture suggests another answer, which is human safety. And this picture itself shows an uninhabited combat air vehicle that's currently in development by the Air Force and the Navy as well. And the objective here is to keep the human pilot, the friendly human pilot, out of harm's way in the operation of a military campaign. And there are similar examples examples such as deep space probes and toxic material handling and bomb explosives and other things, where by employing autonomous systems, we believe we can ensure human safety to a great extent. So at this point, I think some of you may be wondering whether I'm using these terms, autonomy and automation, somewhat fuzzily. And perhaps a few years ago that would have been okay, but fuzziness seems to be a little bit out of fashion these days. Nevertheless, I have to admit that yes, that is the case, and I am not really trying to make any clean, hard distinctions between these terms. I think these terms are, in fact, in some ways inherently ambiguous. And just as an excuse, I have this quote from one of my favorite philosophers, Dr. Wittgenstein. The meaning of a word is its use in the language. So I'll just tell you a little bit about how I'm using the words, and I'll assume that it imparts the meaning that I want to attach to them. When I think of autonomy, and I think this is true in general when we talk about autonomy, I think what's really critical is this notion that the system is able to respond appropriately to unforeseen situations. So if all you're reacting on the basis of reacting with is some precompiled design time canned solution, to me that's not autonomous in any meaningful sense. Now if you look at the state of automation today, in fact that extent of autonomy is simply absent. We can operate our systems completely automatically as long as they're under nominal modes of operation. When an aircraft is flying at cruise altitude without any external weather disturbance, when a refinery or a chemical plant or a unit in a plant is operating at more or less steady state, when traffic flows are moderate, you're not in cities like Rome, the automation seems to work in general just fine. The issues arise when you encounter abnormal conditions, when these canned solutions that you have, whether these canned solutions are intended purely for steady state operation, or whether they are intended for specific fault management aspects that you've already pre-designed. When you are in those abnormal conditions, your automation isn't really able to deal with it, and the human intervention is necessary. And as we start thinking about complex systems such as enterprises, the issue is that you'll rarely find them in steady state or find them in any nominal mode of operation. If you think about something on the scale of a large chemical plant, there'll always be the case that one particular piece of equipment is failing or about to fail, or there's some uncertainty about the raw material that's coming in, or product demand is changing and you want to change your plant behavior appropriately. So the issue then becomes, what are some key new technologies and research areas to enable us to do autonomous and semi-autonomous operational enterprises? And you'll notice I've highlighted semi-autonomous here. And the reason for doing that is I'm actually quite convinced that despite all this talk about increasing autonomy, when we start thinking about ever larger scale systems, the human for the foreseeable future is going to stay in some respects within the loop. And so we have to take into account the human element and in a sense integrate the human element in the solutions that we're developing, not exclude the human element entirely. So with that as background, let me now move to talking about a few selected directions for research and development. And these are listed here. I actually had a bit of fun coming up with this list, and it's not the entire list. I had to cut back, and I'm sure you can think of other areas as well. And what I'm going to be doing is going through each of these. And as I go through them, I'll try and give you some idea of what it is that I mean by these particular terms and buzzwords, and also then give you, in some cases anyway, an example of the sort of research I'm talking about. And in most cases, the research is preliminary, or it's certainly not intended to address all the sophistication and complexity behind any of these areas, but it's just rather an illustration of the sorts of things that I think we can be doing, and some notions of the sorts of results that can be achieved. So let's start with multimodels. I said earlier that to me, an inherent aspect of autonomy is an ability to respond appropriately to unforeseen situations. So the question arises, how can we do that with control systems? And actually, I believe that if you think about this whole notion of model-based control, that really suggests the answer. The only issue is that when we as a community think about model-based control, we think of it in a rather limited context. So it's this notion of model-based control writ large that I think is important to pursue. And when we start talking about applying notions of model-based control to enterprise-wide problems, the model set you're interested in now no longer can be limited to some specific small-scale aspect of the operation of a system. You have to think about the dynamics of the system under different operating conditions. You have to think about fault modes that the system may have. You have to think about the environment that the system is operating in, the objectives that you have of the system. And you have to have some representations of all these sorts of knowledge, some representations that you can explicitly manipulate with your algorithm online. And that's what we do with model-based control in a sense. But now we're talking about doing model-based control with these many different types of knowledge, so in a sense, many different types of models. And this whole issue of integrating these models together becomes rather important. And even if you just focus solely on the behavioral aspects of systems, I think you have to realize that when you talk about problems at this scale of complexity, these behaviors cannot be captured with unitary models, with single models of any kind. We have to be concerned about different types of models that we develop for different conditions, and how do we integrate them together. So just the panel here shows some of the ways that we capture the behavior of systems for different aspects. The first sub-bullet here shows that when it comes to the knowledge that's captured, this knowledge can come from three different sources. It can come from our first principles understanding, it can come from data, it can come from heuristic knowledge. The complexity, there's an algebraic complexity dimension that we can span with our models as well. They can be linear or non-linear. There's temporal complexity. Our models can be dynamic or static. They can be lumped to distributed parameter. They can be operationally localized, by which I mean you can have models that are tailored to specific operating conditions and not others. So perhaps linearized models of particular operating conditions. And they can be structurally localized models of individual components of a multi-component integrated large-scale system. So what I really believe is that we need to be doing more research in thinking about how we integrate these different types of models for different types of applications. And it's not like there's no research being done in this area. There's actually quite a bit of very interesting work that's been going on for some time. So there's this notion of model blending, for example. You can have models that develop for different operating conditions, and now as you transition between operating conditions, you can blend the outputs of the model based on some supervisory weights. A lot of work in the integration of physical models, such as first principle models, with empirical or data-driven models, such as neural networks. This whole notion of hybrid dynamical systems, about which I'll have more to say, is another, to me anyway, example of a multimodal. Even something like a wavelet representation of a signal within a single unified formulation, you can capture multi-scale and multi-resolution aspects of that signal. So let me move on from there to another, what I think of as a related topic, that's adaptive resource management. And when you think about automation at the scale of an enterprise, you have to realize that it encompasses many concurrent tasks. And these include regulatory control, they include supervisory control, they include operational optimization, there may be fault detection that you need to do, fault identification that has to happen whenever you detect a fault, control reconfiguration, reporting tasks, communicating tasks. All of these things need to be done and need to be supported by the computation infrastructure that you have available for the automation. And it's not as if these things are all equally important, and it's not as if these things have some predetermined importance that you can hard code into your resource management approach. In fact, depending on the situation and context that a system is in, some or other of these may be more or less important. So if you have a fault, for example, maybe you want to back off on how much resources you devote to operational optimization and focus more on the fault detection and fault isolation. And from an algorithmic and modeling point of view, we have some ideas of how to do this. Most of the sophisticated algorithms that we develop actually are what we can refer to as anytime algorithms. They are iterative algorithms which can take more or less computing time depending on the degree of fidelity of results required. And multi-resolution models also suggest ways to think about scaling back or increasing the degree of accuracy of some computation that you're doing or some particular algorithmic task that you're attempting to perform. But what we don't really have is a good solution for how the underlying computational resources are to be managed. How should we balance these multiple trade-offs and these multiple considerations as we encounter new situations in the operation of a complex system? And it's in particular the notion of execution requirements of models is something we tend to not focus on as much as the mathematics or the sort of input-output structure. And I've been talking about this in this slide really focuses on the processing and resource management area. There are similar arguments that can be made for memory, communication, power, and some other resources as well. Actually, if you're interested more in this topic, there's a special session tomorrow morning chaired by Bonnie Heck, and we have a paper in that session that talks a little bit more about this whole area of adaptive resource management. So just to give you an example of some work that's in some ways related to these thoughts, this is describing this particular talks about a particular project we have underway in the adaptive resource management area. It's a DARPA software-enabled control project. And what we've been developing here is new ways of thinking about route optimization for uninhabited autonomous vehicles. And we're really thinking about this from a multi-vehicle perspective, but the first work that's shown on this slide is really for a single vehicle. And this is a multi-scale approach in the sense that we're adopting a wavelet-like representation for the trajectory of an uninhabited autonomous vehicle. So depending on which basis functions you engage or disengage, you can change the scale and resolution at different time horizons of your trajectory. Now, once you adopt this sort of a representation, then the optimization problem boils down to coming up with values for the coefficients of the selected basis functions. And we're using an evolutionary computing algorithm to do that. And so this is an anytime algorithm. It'll give you a better answer if you let it run for a long period of time, but in many cases, it'll give you an acceptable answer even if you let it run for not so long. So there's some minimum threshold that you need to let it execute. For beyond that, it's scalable, the results are scalable. And what we've been really interested in is this issue of situation-sensitive adaptation. If you think about a military UAV, you have to sometimes think about avoiding radar, so you want to fly as low as possible. Other times you have to think about avoiding threats, you want to evade threats. You may have a target that you want to capture. And in many cases you have to blend these and other objectives. And this particular animation here shows how this works. And it actually runs pretty fast, so it'll probably run twice before I can even start talking about it. But what we have here is we have some terrain data that's actually from north of Albuquerque, New Mexico. And an aircraft is flying along, and as it's flying, different things happen, and now it has to change what it's doing. It has to change its route. So initially what happens is that as it enters this area, a target pops up, that's the red, a threat pops up, that's this red circle. And so it has to immediately compute a route that evades the threat. And in order to do that, it has to just focus on the short term and forget about the longer term activity and really downgrade the criterion of flying as low as possible, which you want to do to avoid radar. and then it's flying along this threat-evading route, and now a target shows up. This target, I think, is located right over the Santa Fe Institute, but that's purely by coincidence. And it changes its route again. Now it has to do it in different ways. It has more time to do it. On the other hand, it's a little bit more complex problem as well. And otherwise, it's always trying to minimize the altitude of the terrain over which it is flying. So the question is, how are you managing the computing resources, and what does it mean to be managing the computing resources in this application? So the degrees of freedom that you have with these models and algorithms include things like the horizon of the trajectory optimization. You can choose to do the trajectory optimization over a longer or shorter time window, and you can choose to do the trajectory optimization at different resolution levels. The number of iterations you allow your optimizer to run for is another handle that you have. And then some of the models, such as the vehicle model, the terrain model, the threat model, the target model, they can all be multi-scale models as well, so you can spend more or less time on them. This work is also under the DARPA software control umbrella, and actually many of the other projects under that umbrella that are projects other than the one we have are also doing very interesting research, not directly addressing this issue, but other aspects of the so-called notion of autonomous systems and enterprise systems. I should also say that this particular example doesn't really have a lot of focus on enterprise optimization, but I think it illustrates some themes that I think are central to enterprise optimization. Next, let me turn to this topic of coordination of network systems. I've really been rather intrigued by seeing just how much of a buzz there has been generated over the topic of networks over the last several years. We used to talk about complexity as being represented by systems of systems. Now a more appropriate neologism seems to be networks of systems. And it seems to me, in fact, that there's a new discipline emerging that encompasses networks, not in the specific sense of communication networks or transportation networks or sensor networks, but in a more general abstract sense. And a lot of the research that's being done here is not being reported in our journals. It's very good places like Science and Nature, and some examples of this research are listed here. So there's this notion of small world networks. Some of you may have seen this film called 6 Degrees of Separation, or played this parlor game called 6 Degrees of Kevin Bacon. And the idea here is that no two people in the planet are separated by more than 6 people, if you think about the people you know, and the people that they know, and the people that those people know, and so on. It turns out people are, and there are in fact some statistics about that as well now, that you aren't really that far from anybody in the world. So it's really a small world. Those of you who are more into mathematics than Hollywood and Kevin Bacon may have encountered a similar abstraction in the concept of Erdős numbers. And Paul Erdős was a very famous mathematician, of course. But Erdős numbers don't refer to any new concept in number theory, but this notion that if you co-authored a paper with Paul Erdős, you have an Erdős number of 1. If you didn't co-author a paper with Paul Erdős, but co-authored a paper with somebody who co-authored a paper with Paul Erdős, you have an Erdős number of 2, and so on. And I don't know exactly what the numbers are, but I think most mathematicians have Erdős numbers that are actually rather low. And quite likely, I think even in this room, the maximum Erdős number is probably in the single digits. Another topic is power law distributions. So we tend to think that all these phenomena, these random phenomena that we encounter, have normal distributions, and we develop our techniques accordingly. In fact, it turns out that many of these are distributed according to power laws, and there's been a lot of it's been sort of a conundrum about why that's the case. I think the best answer we have right now is that these power law dynamics arise due to the degrees of coupling between what you can think of as nodes in a network and some particular weak kinds of couplings. So there's a lot of interesting work in sort of networks in a general sense, and what I'd like to really see develop is some notion of control of complex networks, and it, to some extent, is already being developed. And when you think about control of complex networks, one way to think about it is that you can have a global, optimal, centralized solution, but really that's not at all practical for efficiency and robustness reasons. On the other hand, you don't want to do this in completely decentralized fashion either, and that's in fact how some of these problems are currently being solved. But in order to obtain the level of performance that you want, you cannot assume that your subsystems are dynamically isolated. So to give you an example of some work that's relevant to this category, this view graph shows a new approach developed by Joseph Liu and colleagues at Honeywell Organization, and focusing on optimization for a refinery-wide system. And this is really looking at dynamic optimization. So when you think about a refinery, and I showed you a schematic of one earlier, there are any number of individual units which are controlled by model predictive controllers. Now the issue is, how do you coordinate the activities of all of these MPCs? Now, in order to do this in a dynamically sophisticated way, you have to assume some additional structure to the models at the coordinator level. So you have to capture some elements of those dynamic interactions. So things are a little bit more complex than they would be with a conventional real-time optimization approach, where you assume that you have a steady-state model at the coordination level and forget about dynamics at that level. But with that conventional approach, you really have to wait for steady-state before you can make any changes. And here now you can make changes even while the plant is moving. And the key notion here is that this coordinator is running in synchrony with the model predictive controllers. So it's specifying not just a target, not just a set point for the MPCs, but because it's running at the same rate as the MPCs, it can actually specify the desired dynamics of achieving those set points as well, taking into account the dynamics of some aspects of the dynamics of multiple systems. Now, the current solution is focused on linear model predictive controllers, and there's a range control algorithm that's been developed, and if you're interested in the mathematics behind it, I refer you to this paper. But it's important to highlight here that even though there's a lot more research to be done and lots of extensions to be made to this has actually been already deployed rather successfully, and in fact the largest implementation coordinates 40 model predictive controllers in an ethylene plant. Next topic is data-centric control and optimization. Now, this whole notion of data-centric techniques is certainly not new. All of identification and empirical modeling can be classified under that. What I think is somewhat new is this notion that now we can use databases, online databases, in real time for doing control and optimization. So we now have databases that are accessible online. Many enterprises will have years' worth of data just lying around that you can access instantaneously. And if you can develop sufficiently powerful algorithms and with the powerful computing capabilities that are available today, you can actually think about doing just-in-time database-driven identification, forecasting, control, and optimization. And the advantage of doing that is now you're capturing process behavior at the time of the decision. You can use the recent data that's available from your database, rather than use essentially a model that was abstracted from data at the time that the model was commissioned, which may have been years ago. So you can automatically adapt as the system changes and runs. And there's a lot of sophistication involved in doing this in the right way, and I won't go into the details of that. But one point to note is this last bullet here, that in fact this data-centric view also provides you a multi-modeling approach as well, because if you think about accessing a database to get all your data for doing any predictions, your database doesn't have to be populated by real data from the plant. It can also be populated by data that's generated by exercising first principles models and heuristic models. So in addition to having a conventional maximum likelihood kind of framework for this, you can even incorporate a Bayesian framework by taking into account first principles understanding through exercising that first principles model with various relevant inputs. And this view graph shows some functions that are currently part of a system that's been developed at Honeywell Labs product laboratory. And there are a number of data-centric functions that are part of this: regression, classification, optimization, and data analysis. But the underlying idea is really rather similar in all of these cases. So if you take the top left-hand box there, what's shown at the bottom of it is a query point. So this can be the state of your system, and you want to be able to predict some property perhaps based on the current state of the system. This property could be the future state, it could be some product property, it could be some performance measure. Now what you can do is you can access the database and try and find all other times when you had a state similar to the state that you're encountering today. So you can do the search in real time over some neighborhood, and you can end up with some number of data points. And now with those data points, you can fit a local model on the fly and use that local model population. So using the most recent data that you have available, yet you're taking care of some robustness issues by making sure that you're smoothing the fit in the right way. And this is showing the case for a continuous target variable. There are similar. You can do this in the categorical space as well. And you can do it for optimization. And now when you think about optimization, your query point now is not just a state. It's a state in combination with some hypothesized possible action. And so you may need to do a database search trying to find other times when in this similar state you did a similar action, what was the result to that. Again, there's a lot of sophisticated math behind it, and I'm going to have to defer to that paper that's cited here for it. This has been operational in the Brno district heating system in the Czech Republic for a couple of years now. This is a fairly complex system. It has 5 plants, which include steam plants and combined heating and power plants, and over 100 miles of steam and water pipes. So that's the scale of the system that's being encompassed by this particular tool. Next, let me turn to control with intelligent adversaries. We are, of course, often talking about control as being concerned with disturbance rejection. But what we usually mean by disturbance is really rather limiting. We think of disturbances as random things that are, safe to say, neutral in some sense. When you talk about optimizing something like an enterprise, however, and controlling an enterprise, you have to realize that your adversaries can, in fact, be intelligent. And the best examples of this are probably in military campaigns, and also in the commercial marketplace, you'll see similar instances too. So you have enemies in the military arena who are trying to do something that's possibly opposed to what you're trying to do, but they're not necessarily completely opposed to it. There may be feints and deceptions that are going on, and so an immediate objective that the enemy may have cannot be simply said to be one of defeating you overall. In competitive marketplace, in some ways, things are even more complex. Instead of having one competitor, one enemy, you have multiple competitors, and those competitors can turn into customers at some point and acquirers at other points, and so on. So it's all very complex. There are certainly some aspects of game theory and robust control that relate to this, but in many ways this work goes beyond at least traditional notions of game theory and robust control. And one thing to note here is that in these sorts of problems, you can always think of some worst-case scenario that could happen, and you really wouldn't be able to do anything about it. You could, if you're fighting a battle, you may send a mission out, and it may be the case that there's always some probability that this mission will end up not destroying anything, and all your aircraft, if that's what your mission consists of, will get shot down. So you can't really just think solely in terms of a min-max formulation and a worst-case formulation. You have to really think about this as a stochastic problem. And it's important also to recognize that at the scale of enterprises, the human is really very much part of the loop, and the human ends up both being part of the controller in a sense, because they're human decision makers that have to be involved, and part of the plant as well. So your actuation, in fact, may involve human forces, and your enemy may have human forces as well in the military scenario. And so you need to really encompass human modeling and human augmentation as part of this overall notion. And this particular graphic here shows one way of thinking about military campaigns from this point of view. So you have a stochastic, unfriendly plant that captures also the behavior of your enemy in this battle space. And what you're doing is you're sending out mission packages. So it's sort of a staged approach in this case. And so your mission package goes out attempting to destroy some targets, and then there's some estimate of battle status, and based on that estimate, you configure your next mission package. And so you have this plant that's really a stochastic plant. On the other hand, your controller cannot really, if it's going to be any kind of typical model-based controller, isn't really going to be able to work with doing large-scale Monte Carlo simulations on stochastic plants. So you have to somehow abstract the behavior of the stochastic plant in some way that's computationally attractive. And this picture shows the progression of one battle, and then this shows 9 stages that are being fought here. And we start out with a deterministic situation where the friendly assets are 4, so 4 aircraft, something that way, and the foe has 11 aircraft. And we have successive encounters, and each of these players lose some aircraft in the process. And you start, and of course, there's uncertainty, so you start with this deterministic state, and things get rather cloudy rather soon. And so, in fact, it's this distribution that's being propagated over time. And under some assumptions, you can actually come up with closed-form solutions that are essentially optimal, even taking into account intelligent adversaries in stochastic environments. Of course, this is, again, limited to some particular kinds of scenarios, and a lot more research needs to be done in this area. Next topic is large-scale optimization. As you might expect, scalability is really key for enterprise optimization methods. Even now, in fact, when people talk about doing optimization at the refinery-wide level, the models that they come up with have something like 1 million variables and constraints, so 1 million equations. This seems impossible to do, but in fact, we have techniques that can address problems at this scale, and these techniques are mathematical programming techniques. I think in part of our community, we think of these techniques as really being rather brute force, and it's probably true to say that they are. But on the other hand, they're extremely effective techniques, and they're widespread in the process industries. There's in fact rather interesting research that needs to be done in this area as well. In particular, current work doesn't really address complexities of dynamics in the right kind of way for optimal control kinds of applications. And so there's this emerging technology of solvers for large-scale hybrid dynamical systems, and these techniques include mixed-media dynamic optimization. and complementarity methods, which essentially try to continualize the discrete space. And there's a fair amount of work going on in this area now, even within the controls community. So Eric Ferran's group at MIT, Manfred Merari's group at HFSU are involved in this work. And this is actually a rather rich area for enterprise-level applications, supply chain optimization, integration of planning, scheduling, optimization, and control, coordinate control are all aspects of this work. I think I'm going to skip my little illustration here that I had. You can go to that paper. It shows how you can solve some large-scale conflict resolution, aircraft conflict resolution problems using mathematical programming techniques. This is an approach that's actually quite viable for any number of aircraft. We've been doing that in conjunction with Claire Tomlin's group at Stanford. And the last topic I wanted to touch on is this area of high confidence control. Many of us, I suspect, have been frustrated at times with the slowness and perhaps in some cases the sheer impossibility, it seems, of getting these advanced control developments that we come up with installed and operating and making an impact in the real world. And in many cases, I would submit that the problem isn't that we haven't done the theory well enough, and the problem isn't that our simulation or experimental results haven't been sufficiently detailed. The problem is that these sophisticated algorithms have to end up working on specific real-time platforms, and how can you be assured that they are going to do what they have been built as being able to do? So we need new concepts for assurance technology that are tailored towards more sophisticated algorithms than we currently have available. If you think about runtime systems today, actually, you may have some really sophisticated algorithm, and you may end up with some people who are responsible for the operational system agreeing to implement these algorithms. But what typically ends up being implemented is some PID-like version of that algorithm. A lot of the complexity ends up being abstracted away. So how do we get these more sophisticated behaviors incorporated into systems? And so we need new concepts for verification, validation, certification, where appropriate. And one particular area that I think is rather important to pursue here is getting away from this notion that we want to be able to specify with 100% certainty that this thing is always going to give you the result within the amount of computing time you have available, and recognize that we have to live with probabilistic results to some extent. We've already admit to that with machinery of various sorts. The equipment that we use has some 99.999% perhaps likelihood of reliability, but it's not much more than that necessarily. So even for the algorithmic space and implementation of complex algorithms, we have to go in that direction. And we are currently in a DARPA software-enabled control project applying these sorts of notions to some hybrid model predictive control developments. So at this point, I'm going to talk a little bit about something completely different. And I actually thought long and hard before deciding whether to put this in, and after you listen to me, you may think I didn't think long and hard enough. But as I said, being plenary speaker gives you some license. So the topic of interest here is consciousness. And the reason I wanted to bring this up is that whenever we talk about autonomy in the context of biological systems like humans, it's actually very similar to how we talk about this whole notion of consciousness. So we talk about ourselves being aware of our goals, our capabilities, of the situations that we're in, and of being able to adapt our behavior accordingly, taking into account our limitations, our cognitive limitations, our physical limitations. And that's certainly part, if not parcel, of the notion of consciousness that we also use to describe ourselves. So it's actually a small step from there to ask the question, will we have to endow our engineered systems with some elements of what we really call consciousness? There are actually some complicating aspects that come into play here. We know that there are fundamental limitations of digital computing. There are problems that are undecidable. We know that this mathematics is incomplete, and that has a significant bearing on what you can do with digital computing as well. And the question arises in the minds of many people, are humans prey to these limitations? And if not, then maybe there's something completely different going on, and if so, then how do we deal with that? And there's in fact a lot of interest in the philosophy community and the AI community and some other elements as well, some elements of the control community too, in fact, on this notion of computational consciousness. And I just have been doing some reading on this area, so I thought I'd show you some of the critiques of the computational consciousness research program. These are some examples of why people think it's not possible to have consciousness in any computing entity. So first of all, there's this argument that there's something special about analog processing. Now we have the Church-Turing thesis, which says that anything computable is digitally computable. But that is just a thesis, it's not something we can prove, or we we can hope to prove even, in fact. So some people say, well, there's something so special about analog processing that digital computers can't do it. If you could develop analog computers at the same level of capability as the human brain is, perhaps, then perhaps you could have conscious computing. Other people, and the principal example here is Roger Penrose, say that there's something special about the biological substrate. And Roger Penrose thinks that there's quantum gravitational effects going on in the brain that allow you to do conscious processing and overcome the limitations of digital computing. I haven't really come across any evidence of this quantum gravitational effects going on in the brain, but I'm not a biologist. There's also an argument that consciousness is a product of embodiment, that the only way we get to be conscious is by being formed in some developmental environment. So we grow up in an environment, we learn to adapt to an environment. It's all somehow so nebulous or complex that it's inconceivable that you could capture that in some digital system. So you have to have something that's not programmed, but that's self-learned. And finally, there's also some thought that consciousness is simply a vitalistic phenomenon, that it's something mystical, there's nothing you can do about it. So I have personal views on lots of these things, of course, but I just sort of give you a really non-controversial, I think, personal view here. And that is that we will, in fact, I think, be engineering aspects of what we call consciousness as we develop technology for autonomous enterprise-wide automation and control. So let me finally just conclude. I've tried to show you that the enterprise is getting to be an increasingly important focus for industry-related research in automation and control. This covers the space from process plants to supply chains, to military teams, to power grids, to airspaces, to large-scale facility management systems. Systems and control concepts and expertise are critical to success in these endeavors, and this is not just me saying it. In fact, I sometimes get the impression that the systems and control community is being dragged kicking and screaming to solve these problems. Everybody else who's trying to solve these problems thinks that systems and control concepts are key to them, but we tend to not have somehow gotten that message as yet and are happy doing our more traditional research. Having said that, though, it's also important to recognize that there are new directions for research that are involved here. So there's a lot of exciting research that could be done that builds on our established foundations. And actually, as I was looking over these various topics that I put together, I realized that there were some key core concepts that were falling out of many of these topics, and in particular, model predictive control and hybrid dynamics, I think, are sort of centerpieces or linchpins for this entire new edifice of automation and enterprise optimization. And finally, the complexity of problems is such that you cannot hope to address these issues with any sort of discipline-centric kind of perspective. You have to really adopt multidisciplinary, multi-institutional perspective and collaborations. I don't know if you want to go all the way to including philosophers in your community, but there may even be some merit to that. And finally, here's the reference, and of course you can get in touch with me if you don't have a pen handy, and if you want to follow up on this. And I would also like to thank many people for material and comments that have helped me put this material together. Thank you very much.
Thank you very much, Tariq. It will be interesting to compare the program 2005 ACC with some of the things you predicted here. Before you leave, I'd like to make an announcement about this evening session. At 6:15, there's a special session on the history of control, which will be here in Salon 4. And we are really privileged to have the speaker that's going to be here. Otto Meyer is former acting director of the Smithsonian Museum of History of Technology. He's currently director of the Deutsches Museum, and in 1970 he wrote the book on the history of feedback control. A very nice compliment to what we heard today. So I hope that's at 6:15 right after the sessions. And also remember, if you are not going to the luncheon today, if you could drop your ticket off at the registration desk, that would be much appreciated by students who would like to attend the luncheon. Thank you.